So when we look at the parent graph of the absolute function here, we can see that really it exists in two parts or pieces. You got the first part, if you're reading it from left to right, where x is less than 0, and that's going this way. And then you got the next part where x is equal to or greater than 0, or going this way. And this here, if I take the slope of this graph and I write the equation of the line, I would see that for this part, y is equal to negative x. And that's because it goes down by 1, over by 1, down by 1, over by 1. And so it's negative 1 over 1, or negative x. But then for this part, if I were to get the equation of the line, take the slope and everything, I would see it goes over by 1, up by 1, over by 1, up by 1. And so y is equal to positive x. And so the original absolute value function really exists as a combination between these two functions. Y is equal to negative x meets y equals x, and together they meet to make this giant function over here. You could think about each of these as a piece, where this is the first piece and this is the second piece. And both of them come together or piece together to make our absolute value function. So a piecewise function is a function that changes the way it behaves at certain x intervals. We call these changes and behavior pieces, and these pieces come together to make one giant function. And if you think about it, the most classic example of a piecewise function would be your absolute value function. Because as we demonstrated on the graph, when x is negative, it behaves like f at x is equal to negative x, right? A downward sloping motion. But when x is positive or greater than 0 in general, then it behaves like this. It goes straight up, and it behaves like f at x is equal to positive x. So these two pieces, or two different functions, come together to make this one giant function. So absolute value functions are indeed piecewise functions. Now, how we write piecewise functions is a little different. We go f at x is equal to, and we set the conditions where it behaves like x whenever x is at a certain interval, and it behaves like x squared, for example, when x is at another interval. And it really just depends on the function itself that is formed. And you can have up to 3-4 different pieces going on in one function. So when we're writing absolute value functions as piecewise functions, we follow their general nature, which we could see from the graph. And so we'll express it like this. F at x is equal to x when x is greater than or equal to 0. So from here to there. Or negative x when x is less than 0. Or that downward sloping line over here. Now what that negative means is that whatever is written inside the absolute value bars over here, you're just going to multiply all of that by the negative 1 in front. Another thing to point out is that we wrote zeros here, and that's because we're talking about the original parent function. However, these things can be transformed or translated as well. And so we're not going to always refer to x being greater than or equal to 0 or less than 0. Sometimes it'll be another number based on how it's been translated. And so what we say is that in order to get this proper notation, we're going to set the absolute value bars, so whatever is inside these bars, kind of like brackets, to 0. And that's another way of saying solve for x within them. And so if I look at this example here, I got x minus 2. Well, if we set this to 0, and we go x minus 2 equals 0, which means that x is really 2, then our notation here is going to be greater than or equal to 2 and less than 2. And so when we want to write this as a piecewise function, we're going to follow this general notation, but we're going to change the zeros to 2's. And so if I'm writing this as a piecewise function, it's going to be f at x is equal to. Now, when I say x, that means that it's just going to be the original function inside the absolute value bars, right? There's nothing that's being multiplied or taken away, so it'll be x minus 2 when x is greater than or equal to 2. And then it's going to be negative x minus 2 when x is smaller than 2. For a second example here, we've got f at x is equal to absolute value of 2x plus 1. So like we did the first time, we're going to set the boundary or find the boundary of where this has been translated to by setting these absolute value bars to 0, kind of like what we do with a bracket. So 2x plus 1 equals 0. And if I isolate for this, I would get x is equal to negative 1 over 2. So this is going to be the boundary that we're working with. And so, like we did before in general form, we got f at x is equal to, and it's going to be 2x plus 1. And that's going to be when x is greater than or equal to negative 1 over 2. And then it's going to be negative 2x plus 1, which we could really rewrite it as negative 2x minus 1 when x is going to be smaller than, let me just write that again, x will be smaller than negative 1 over 2. And this is the piecewise function for both of these absolute value functions.